In this tutorial, you will explore a visual representation of the slope of a sine function. First, you'll construct a secant line that moves along a sine function. Next, you'll trace the slope of the line as a function of x. Finally, you'll drag the points on the function closer together to better approximate the slope of the sine. You'll also create a movement button that brings point B to point A. To start my slope investigation, I'll graph a function, f of x equals sine of x. I'll begin with a new sketch and choose Graph, Plot New Function. So here I have Sketchpad's calculator, and I will choose sine, and then click on X, and then click on OK. A dialog box appears asking if I'd like to switch my angle units from degrees to radians. Since I'm graphing a trig function, I'll say yes. Here's my graph, f of x equals sine of x, and I see that the x-axis is labeled in terms of units of pi, and there's a point here. This is the unit point. If I drag that point, the scaling along my x-axis changes. There's also a unit point along the y-axis. If I drag that, my y-axis scaling changes independent of the x-axis. To continue, I'm going to construct a secant line along my graph. I'll begin by going to the straight edge tool and choosing the line tool. Next, I'll move directly over my function so that the function is highlighted. This indicates that I can place one point that defines the line along it. I'll click and then move to any other place along my function to place the other point. Now I have both points that define my line attached to the function. Finally, I'll drag the points so that they're fairly close to each other. There. Okay, now I am ready to animate my line. I will select the line and choose Display, Animate Line. My line begins to move along the sine function, and not only that, but a motion controller appears here, which allows me to change the speed of the line. I can also click on the Stop button to stop the movement of the line entirely. Now that my line has stopped moving, I'm going to measure its slope. I'll select the line and choose Measure, Slope. The slope appears. If I now drag point B, as my line moves, the slope changes. The question I'd like to think about now is, how can I measure the slope of the sine function at a particular point along it, in this case, at point A? Well, right now we have a line passing through point A and through point B. And intuitively at least, with point B so far away from point A, this does not look like a good approximation of the slope of the sine function at point A. So perhaps I should drag point B so that it's closer to point A. Now with these 2 points closer together, I'll select the line again, and I'll restart its animation. As the line moves, the slope again changes its value, and I'm getting what looks like at least a fairly decent representation of the slope at point A itself, as point A moves along the sine function. Right now, it's a little hard for me to interpret what's happening with the slope of AB as the line moves, because all I can really look at is its numerical value. It would be helpful, I think, if I could actually somehow graph this so I could view it visually. So what I'm going to do is select point A and choose Measure, Abscissa X. This measures the x value of point A. Now I'm going to select x of A and the slope of AB and choose Graph, Plot as xy. This takes those two values, the x value of point A and the slope of AB, and it plots it on my graph. Notice that that point sits directly below point A. That's because it has the same x value. Let's set the line back in motion. I'll select the line and go back to the motion controller and start it back. Notice now that as the line moves, that point, the one we just plotted, moves along with it. Its y value represents the slope of the secant line as the secant line moves along the function. This is better, but there's still one problem. I can't see the entire graph that's being traced by this point. So let's stop the line once again. I'll select this point, and in order to view it as the point is moving, I'll choose Display, Trace Plotted Point. Now I'll select the line again and set it back in motion. Now that point, whose x-coordinate is the x-coordinate of point A and whose y-coordinate is the slope of my secant line, leaves a trace behind. As my line moves back and forth along the curve, I can view this trace and see if it resembles any function that I know. To continue, I'll stop the animation of the line by pressing the Stop button on my motion controller. Now I'm going to erase all of the traces on my screen by choosing Display, Erase Traces. They all go away. Remember before I was talking about how we could best approximate the slope of the sine function at point A. When point B was far away from point A, the slope of our secant line seemed to do a very poor job of approximating that slope. As B gets closer to point A, at least intuitively, the line seems to do a better job. Well, right now point B is still kind of far away from point A. So I'm going to drag it so it's even closer to point A. And now that they're close, maybe we can get an even better approximation of the slope when we animate the line. This time though, let's animate the line using a different method other than using the motion controller. I'm going to select points A and B and go to the Edit menu and choose Action Buttons, Animation. I'll then click OK, and I have myself a new button called Animate Points. When I click that button, my secant line begins to move, and if I click it again, the movement stops. I'll start the motion once again. Now you can investigate this new graph traced by the point that represents the slope of the line and see once again if it resembles any function that you know. Okay, so I'm going to stop the motion again, and let's see. I'll move these points a little bit farther apart so we can see them. Now, as we move the points closer and closer together, we get a better and better approximation of the slope of the graph at point A. Well, what if we could move the points so that they were directly on top of each other? This is the best we could do. So I'm going to select point B, and then select point A, and choose Edit, Action Buttons, Movement. And I'm going to now click OK. This button moves point B directly onto point A. Let's click that. Well, when I do, because the points are directly on top of each other, there's only one point now, technically, that's there to define a line. And the line needs 2 points. So we no longer have a line. This is interesting though because it points out this notion of limits when we start talking about calculus. What happens to the line and its slope as point B gets closer and closer and infinitesimally closer to point A? Well, for now at least, let's drag these 2 points apart so that our line reappears. The Explore More gets more into calculus and introduces the derivative.